When we start thinking about the things that are going across the wire and how they can be optimized, how we can maximize our use of the wire, um, you have to take a look at the stack that's being used. And the stack these days is almost always some variant of a LAMP stack, right? Linux, Apache, MySQL, and PHP. And Linux, okay, Linux is a given. Uh, but the Apache part, that that is the part that is forcing statelessness on us, right? And it's not Apache's fault. It's not. It's the way that the system was designed, and the web servers are just the web servers that are doing exactly what they're supposed to be doing. But if there were a way that we could put a stateful system in front of Apache, might we be able to bypass a lot of the data that has to be thrown on the wire um, in favor of some sort of a caching system? And so that's what we did. Uh, we moved Apache one level down so that it works off port 8080 instead of port 80. And on port 80, what we did was put our own program. Now you have to remember what a frognet host is and where it lives in its physical topology. The frognet host is the gateway to the network below it, and from the network below it to the rest of the world. Anything that is being sent from any device attached to the projected network must go through the frognet host to get outside. Even if it's going from one node on the Ethernet to another node on the Ethernet, it still has to go through the frognet host. So if we put an IP tables intercept on the frognet host that traps all port 80 traffic, we get everything coming from all hosts across the entire network. Sort of like promiscuous mode, but not quite. And so by trapping all of the port 80 traffic coming across the network, we can take a look at it and decide what to do with it. If it is not LAN-based traffic, then we just move it on, right? We send it on because that means it's going to the regular internet. It's going to an upstream, something we don't control. But if it is LAN-based traffic, if it is going to another Frognet node or something on another Frognet host, then what we do is establish a permanent socket in between the two machines, in between the two systems. We go from the proxy on one machine to a daemon on another machine. And we open up, it's actually two permanent sockets that go back and forth. But what this does is it saves us the overhead of creating and tearing down a socket every time. So that's one of the first problems I had with the way that we're doing business now, is that we have to create and tear down a new HTTP request every time. And an HTTP request, although we try to use caches and things like that, it's not guaranteed, and you may well end up building a brand new socket. So I didn't want to do that. So using a permanent socket, let's just get rid of that. It's just there. And then we own the socket too. And so we can put our own wire protocol on it. We'll get to that in a little bit. But by owning the socket, what we can do is send our own messages back and forth, and the messages that we send back and forth can be the compressed data based on the templates that we got when we saw the original HTTP request and reply. So we see the request, we turn it into a template, we identify the dynamic elements on it, and then we send that over as it's like request raw, something like that. Request full, I think, is actually what it is. We send that over, and on the other side, it creates a cache entry for it. It identifies the dynamic elements and all things like that. And so the next time we send that request over, we either send request diff with just those things that are changed, or request same, which means run exactly that same query again. And on the other side, when we pick it up, if it's a request diff, then what we got with it was a little map that told us which of the dynamic elements changed, and then the dynamic elements. There's no equal signs, no curly braces, no quotes. It's just the data sitting right there on the pipe, right behind the map. So the map and the data go across, they get rebuilt on the other side. The full request then is submitted to the Apache server on the other side. So we took a full request, figured out what the diffs were, sent only those across the wire, rebuilt the thing, and sent that down to the Apache server. We let it go ahead and do what it's doing and come up with whatever answer it has. And we do the same thing on the way back. We look at our cache, we say, do we have this reply? And if we don't have the reply, then we learn the template of the reply. We learn what elements are going to be likely dynamic inside it. And then we ship it back and we say this is a reply new or reply full, I think. And that causes us to create the cache on the other side. And then the next time we send it, if it's the same, we just say reply the same. And by doing that, we seriously cut down on the amount of stuff flying over the wire, because we don't have to anymore. And that in and of itself gives us actually a performance improvement that we can see, as well as a significant reduction in the overall throughput. So let me show you what I mean, because this is kind of cool, actually. We're sitting here on Seattle 5. This is Seattle 5 here. And this is New York 1, I think. Yep, New York 1. This is Seattle 6. Now, first thing I want to show you is just exactly what it looks like on to the machines. And if I can ever get this window resized, there we go. Nope, wrong one. That one. So you can find it just by doing a journal control. So you do a journal control -u frognet-proxy -u frognet-daemon. And then I'm also going to do a -u frognet-tunnel daemon v3. Now on this machine, it's not going to do anything for that, because that is the daemon that keeps track of the WireGuard tunnels and things like that. This machine doesn't have any WireGuard on it, but that's what I would put in. I mean, I just do it out of habit. it doesn't hurt. The daemon's actually here. But we do that, and then we just say, I do a dash dash no dash pager, so it prints out the full, actually, error name. And then we're just going to do a dash F so you can see this live. And we're going to let it run for just a second here. What you're seeing is the actual, live work that the daemon and the proxy are doing. And you can see here's a RTT ping. Here's a request diff, request miss, request full. Here's where we're receiving a sequence number, 21 bytes. That's a same. Here's a diff with 31 bytes reconstructed. This is happening all the time. And if you look at this with respect to Daemon, which is a network monitor, we can look at the details. And what we see is that here on ETH0, well, first let's look at the topology of this machine. So we have WLAN 0 and WLAN 1 are in use. ETH0 is not in use. WLAN 0 is the identity for the machine, so this is what ETH0 would be. This is the machine, this is the interface that is projecting the network this machine is managing. And then WLAN 1 is our upstream, so this is who we're getting our DNS and the other things through. So if we look at Daemon again, with that in mind, we want to see what's going on in WLAN 0, which is what's going on our own network. And it's really nothing. There's nothing going on here. And on WLAN 1, right? So this is on our upstream network. These are all measured in kilobytes, 9.71 kilobytes per second, 7.7 kilobytes per second. Okay, we're going to crank that up. You saw the pipe workload test yesterday. Now, this is a tribute to what we can do with being able to use FrogNet memory instead of sending messages. I looked at the pipe workload test that we had yesterday, and I decided I wanted to modify it. I wanted it to show me the actual throughput, or not the throughput. I wanted it to show me the bytes saved in addition to the throughput. So I did that, and it took me about an hour. I didn't have to create any new messages. I didn't have to do anything other than say, give me this memory. I did have to modify the proxy, but I was able to get it modified in place, tested, and all set up and distributed across my network in less than an hour. So what we're going to do now is we're going to use that test. We're going to do a pipe workload Seattle 6. So it's FrogNet host Seattle 6. Seattle 6. And the first thing we're going to do is a chat test. Yesterday we did an echo, and an echo was exercising the same diff protocol with all the same. We're going to do this with 200. So the chat test is approximately 200 of these, and every message is going to have a new message rate. It's going to have more differences in it. So this one has 12 differences and 13 the same. So this is simulating more chat, is what it's doing. And here we can see that I added the bytes sent, bytes without the engine, and then what I'm saving. And this is the thing I wanted to show you, is that here, this is the first one is a run to Apache on the 8080 port without having any FrogNet involvement at all. We ran 25 of them. We got 2.7 requests per second through. Then we did exactly the same thing again, but going to port 80 using FrogNet instead of 8080 going straight to Apache. We were able to get, instead of 2.7 requests per second through, we got 8.5 requests per second through, and it took us 6.1 kilobytes total to do that instead of 414 kilobytes, which is what it would have taken if we had sent entire messages. So then we ramp it, and then here is the concurrent test with 200 simultaneous. All 200 succeeded. 166 of them had different contents. 34 of them had the same content. We were able to get 40 requests per second through, and we only had to send 17.2 kilobytes of data for that entire 200 thread system, and we were able to save 99% of the stuff on the wire. So 99% of the bytes on the wire were never transmitted. So we got 188 times the performance of in terms of memory. That is almost unbelievable, and I'm pretty sure that every one of you is going to want to run your own tests and make sure that my numbers are accurate. And I say that because I didn't believe them the first time either, and I had to run it, and I had to look at the logs, and I had to convince myself, but it's real. Those numbers are accurate. We went from from 5 megabytes to 28 kilobytes, and that's not a joke. That's real savings. So just by using FrogNet, you're making your networks more efficient, and you're reducing the bandwidth that you're required to use, and you haven't lost anything. You're gaining. So this is the megabyte test. The megabyte test is a little bit different. It sends a 1 megabyte workload through the system, and that 1 megabyte workload on let's see, here it is. Okay, so this is the 1 megabyte workload here. I'm sending 200 of them. I was able to get 0.5 requests per second through, going straight to Apache. With FrogNet in, I got 3 requests per second through, so that's 6 times performance. In the ramps, I'm not. So in the ramps, I'm getting 8 to 9 requests per second through. And in the burst, the 200 burst, I got 8.8 requests per second through. I did have 21 timeouts on it, but instead of sending 222 megabytes, I sent 23 kilobytes, right? I mean, 23 kilobytes literally. And look at the transmit. This is all in kilobytes. This is what's going on Seattle 6. This was the target of these. So the numbers aren't lying. This is saving what it really is saving, and that's just like incredible in and of itself. But then we add in the network shared memory capability and all the rest of it, and we are looking at something that really moves us from that assembly language quagmire that we were in to be something much more elegant, where we can uh, actually create meaningful things without having to do all that low level work. So next one, we're going to look a little more deeply into how the semantic engine works, how we get from being 367 megabytes to 126 kilobytes. But I want to show you this and get you to understand exactly what we're doing here in terms of saving memory and saving time. All right. See you in the next one. Have fun.